All right, so we're just quickly running through atmosphere. So for atmosphere, we you should focus or we focus on ozone. So you should at least know the importance of ozone. In terms of the importance of ozone, it is
Yeah, it blocks the UV light or you know.
prevented from reaching the surface of the earth. Specifically, ozone is helpful when it is in the stratosphere. If it is in the troposphere, it is not helpful. And it will come up further in the recording.
Yeah,
So what
so the formation of ozone now. So we know say we have oxygen up there, right? What will happen? The oxygen molecules split by UV light, we call it a photolytic reaction to form two radicals of oxygen atoms or oxygen. Yeah, that's it, right?
Yeah.
All right, then the oxygen radical will, because it's so reactive, will react with the oxygen in the air again to form ozone.
Right. So on the past paper, if they ask you to write equation to show the formation of ozone, these are the two equations that you must know. Oxygen molecule to a radical, then the radical reacts with a molecule to give ozone. So you must know this reaction. And again, ozone blocks out UV light and it is in the stratosphere. Hold on. They can ask you for harmful impacts of UV light on human. Two main ones,
skin cancer and the development of cataract. Also skin burn, and it make you be less resistant to certain diseases.
All right, so that's two more. Then no, this one, explain how the concentration of ozone in the atmosphere is maintained. So in explaining the maintenance of ozone, ozone can be produced and it can be broken down, right? So as we showed you above, these are the two equations to show the formation of ozone. We should have UV light above this arrow. Um, mm, So UV light has to be there. So this is showing the formation of ozone. And then now UV light can also break down the ozone to give you back oxygen. So ozone is maintained in the atmosphere when it is produced and then when it is broken down. So it is like a balance, forming the ozone and then ozone is broken down. And UV light is responsible for these reactions. So it is constantly being formed and broken down. So it's like a cycle, right? So that is, so you would use these equations in your explanation. All right, and next point. And next point for ozone, they can ask you to discuss the environmental significance of chlorofluorocarbons in the ozone layer. So chlorofluorocarbons, they actually deplete the ozone layer, right? So the environmental impact of chlorofluorocarbon is that they deplete the ozone layer. So if you're asked to explain this, you are going to do these equations, all right? So this is an example of a chlorofluorocarbon. First thing that will happen is that UV light will break a carbon to chlorine bond. Don't need to know the mechanism. So the UV light, let me pause. All right. So the carbon to chlorine bond is broken. So you get a radical. All right. So the carbon, that is where the that here comes from, and the chlorine radical. All right. Carbon to chlorine bond is broken. Good afternoon. Right, so these, sorry, resume. Right, so once you get the chlorine radical, it is going to it's going to it is going to react with ozone, right? And you get this radical. So just remember these two equations. All right. Next now, you should know effects of ozone and on human beings. And I stated two of them here. All right, so ozone can have positive impact and a negative impact. When it is in the stratosphere, it blocks the harmful the harmful ultraviolet light. Right? So that's a positive impact. When it is in the troposphere now, that is where the negative impact comes into play. It can cause respiratory issues such as asthma and bronchitis. And also it has an harmful effects on the heart and blood vessels. It said it can lead to atherosclerosis. So it clog up the artery, basically. All right. And it also contributes to photochemical smog. Right? And I put the definition there. So for this one, the nitrogen dioxide starts it off. It interacts with UV light. So as you should know by now, UV light is breaking up the molecules to generate a radical. So the NO2 is broken down into nitrogen monoxide and the oxygen radical. Radical reacts with oxygen to give you ozone. And then ozone again interact with NO to give NO2, which is the brown gas. Right? So for ozone or for atmosphere, just remember these equations. How to form an ozone, those two equations. Ozone is balanced in the atmosphere when it is produced and then broken down again. Right? Once ozone is in the troposphere, it is not good, it will cause harm. Right? You should know those equations. Also, you should look at the greenhouse effect and global warming. All right, so the contact process, which is the sulfuric acid reduction, it's almost exam time, right? So if you need to swap, ensure you remember the raw materials, which is sulfur from sulfur in the ground, air, and water. So you must at least know the raw materials, the three stages: sulfur burning, SO2 conversion, and absorption. So those are the three stages. For sulfur burning, it's a simple combustion reaction. So sulfur plus oxygen give us sulfur dioxide. Sulfur conversion, that's the important one. This is the important equation that several questions can stem from. All right. And the reason why it is an important equation, as you can see, it is an equilibrium reaction, and the enthalpy change is negative. All right. So delta H is a negative number. Le Chatelier principle will come into play. All right. So the sulfur conversion, this equation is important. All right. And adsorption. So try and remember these equations. Three process, the raw material, and the equations. Apart from that, you need to know the conditions. So any question, if it should come on this, it will most likely ask about the conditions, the equations, and the raw materials. So the condition now, for 50 degrees Celsius, atmospheric pressure, and the catalyst, vanadium 5 oxide. Formula V2O5. Here now we're going to look at Le Chatelier's principle. So the actual conditions, 450 atmospheric pressure and the catalyst. The ideal condition or the theoretical condition, low temperature and high pressure. And we will have to use the Chatelier's principle to explain it. Now, apart from that, you must know the use of SO2. So you can swap 2 from the video. The use of SO2, and this was not scanned properly. All right, this is the use of sulfuric acid. So it can be used as a catalyst, cleaning agent for metals, fertilizer, dyes, and paint. The impact on the environment can cause acid rain, acidification of this soil. So that's 2. You just need to know at least 2 of each. Only thing I'm going to explain now is the Le Chatelier principle. All right, so you should know the principle and how to explain it. All right, so here's the equation. And as again, it's almost exam. So just swap this. Ideal condition is low temperature. All right. The reason why the ideal condition is low temperature, when the temperature decreases, this is what you will put. If they ask for the ideal or theoretical condition, it is low temperature. The reason for that, one, the forward reaction is exothermic. So this is what you will say. Forward reaction, Rx is short for reaction. Because the forward reaction is exothermic, a decrease in temperature, a decrease in the temperature will shift the equilibrium, to the right. But just remember that when you decrease the temperature, equilibrium will shift to the right hand side. And as you can see, on the right is SO3. So you will increase the yield of SO3. But decrease in temperature, shift the equilibrium to the right, resulting in more SO3 being produced. All right, that's that. For pressure, it is favored by high pressure. For high pressure, if you increase the pressure, the equilibrium is going to shift to the right again. So if you increase the pressure, pressure, the equilibrium is going to shift to the right. So that is what you need to remember. Increase pressure, equilibrium, shift to the right. More SO3 is produced. Right? So that is that for Le Chatelier's principle. And this principle, Le Chatelier,
I want to know right for me.
if a stress is applied to a system at equilibrium, a stress is applied to a system at equilibrium, equilibrium shifts in a direction to counteract the stress. All right, that's that. All right, for UV, let me just mention this. Lambert's law. A equal ECL. You can get a graph to plot. If you get a graph to plot, it will be absorbance, versus concentration. You are going to get a straight line. All right. For this, if they ask it like this, you will have a sample, right? So you will be trying to find the concentration of this sample. So you will have standard solutions, right? And you take the absorbance readings of the standard solutions, and then you take it for the sample. If you want the concentration for the sample, you're simply going to extrapolate it. So you draw a line. So let us say the sample, it has an absorbance of 0.51. You would find 0.51 on the y-axis, draw it to the line, and bring it down. All right. So that is how you would get the concentration of the sample. All right. So this is how you get a calibration. This is called a calibration curve. Not because it is called a curve means you're going to get a curve. It's a straight line. But it is called a calibration curve. Good. All right. They can ask you how to prepare a sample. Right? If you want to find the concentration of a substance, right? All you're going to do is make a series of standard solutions. Shamika, make a series of standard solutions. So if you want to analyze a sample, once you make a series of standard solutions, you're going to place it in a cuvette. Right? You're going to place a small amount of it in a cuvette and place the cuvette in the spectrophotometer. So for UV vis analysis, we use a spectrophotometer. So you put the solution in the cuvette, put the cuvette in the spectrophotometer, and record the absorbance reading. So you would record the absorbance reading, and that's how you would get your calibration curve. The principle of UV vis. If they ask about the principle on which UV vis is based, it's what in terms of electrons. It's in one sentence. It's electron transition. Yeah, electron transition from bonding to antibonding molecular orbital. So bonding is down here, antibonding. Yeah. So electrons move from bonding MO to antibonding MO. All right? That is the basis. Electrons absorb, electrons in your bonding molecular orbital absorb the energy, move into the antibonding. right? For IR, bonds absorb IR, all right? So the principal IR, it's the bonds in the compound that absorb the IR. For UV, it's electrons that absorb UV. And bonds, there are two types of IR vibration. Oh, that. Sure. Right. So there are two types of bond vibration. If they ask for it, it is bond stretching and bending. Just a second. Yeah.